So, we have seen that we can do this interpolation of the lower and upper boundaries, but then, as we saw here in the figure, then the left and the right boundaries get wrong. But we can first write them what we get. When we do this interpolation, then the interpolated left and right boundaries will be following. First, the left boundary that we have there, we have already plotted it. That is for psi equal to 0, and that is function eta. And then we write what we did. We have then 1 minus eta. Then we have the x1 for psi equal to 0 plus eta x2 for psi equal to 0. And then from our identification of the corner points, we see that this here is A, xa, and this here is xc. So then that is what we had the function 7. We then see that this is 1 minus eta xa. So it is a linear interpolation between the values of our grid points at A and at C. Likewise, we can do it for the right boundary. Look what are the interpolated coordinates then for psi equal to 1, function eta. Then we get 1 minus eta. Then we have here the x1 of psi equal to 1 plus eta the x2 psi equal to 1. And then we see the x1 of psi equal to 1 is b, and the x2 of psi equal to 1 is d. So then we get a linear interpolation between our coordinates at xb and xd. Yes. So then that is the result what we get here. That is the result for the left boundary, and that is the result for the right boundary. Now we see from the sketch that we have errors, unless we would have straight lines in between, but in general we will have errors. Now we identify these errors at the left and right boundaries. Left and right R, and that is then first at the left boundary 10a, that is the call it E3 of eta, that is then the correct value x3 of eta minus the interpolated coordinates, which is the x int. What we have seen is for psi equal to 0 eta. So that's the error that we have on the left. So it's the exact one. So the exact one is here, and then the corresponding one is here. So that's then the error. This minus this. Correspondingly, at the right boundary, we have then the error, we call that the E4 of eta. That is then the x4, that is the correct right boundary, minus the interpolated right boundary, which is psi equal to 1 of eta. So the idea is to eliminate the errors that we simply add to the interpolated coordinates, we add the errors. So if we have that, you can see it immediately. If we do that, if we have the interpolated coordinates and we add that at the boundaries, we will get interpolated plus exact minus interpolated, we will get the exact coordinates. So that is the idea. So to eliminate the errors, we add them, but before we do something different, because so far we have only defined the errors at the left and the right boundaries. So we have defined it for the left and the right. So the first thing is that we interpolate these errors. To eliminate the errors, we interpolate them. So we first interpolate them. And that is then the following, that we say now we get a function then for the error, that is a vector, as you see, a function now of psi and eta. So we interpolate them now between the left boundary, that is the E3 of eta, and the right boundary, psi, that is the E4 of eta. So then we have the errors defined in the whole domain. And now we can do what I said. We add then the interpolated coordinates and these interpolated errors, and then the errors are gone at the boundaries. Boundaries are eliminated. For example, if we look for the left boundary, we would have then the interpolated coordinates at the left boundary, psi equal to 0, eta. That is our yellow line here on the left. That is that one. Now, if we add there the error at psi equal to 0 and eta, then we get the interpolated, we write it below, we get then the interpolated coordinates there, so that is just, I repeat that, and now we write down what the error was. And the error was then, if we are at psi equal to 0, here you see the definition of the error, you find the whole domain, then we are at E3 of eta. So then we get this expression here. So then we get then the E3 then is the following, that is then the x3 of eta minus the interpolated coordinates at psi equals 0 and eta. And then you see then the interpolated coordinates cancel and we get the correct left boundary, which is the x3 of eta. Now it's disappeared below, but this is the x, that's the correct x3 of eta. And similar at the right boundary. So then we get the left and right boundaries right, the lower and upper they were right from the very beginning. Of course we did the interpolation between them in the beginning. And now we then can simply see what we get when we do this, when we add the interpolated and the error. So, and that is then the final transfinite interpolation when we do that. We add the interpolated coordinates between lower and upper and these errors where we have corrected at the left and right boundaries. So then when we do that, then we get the final interpolated coordinates of the transfinite interpolation. That is then the following. 12. That our coordinates then are a function of psi and eta, and we take the interpolated coordinates of the first between bottom and top, and then we add the error where we have corrected such that the left and the right boundaries are correct. So if we write out what this is, then we just use the definition of the interpolated coordinates and the definition of the error, and then we can see that. So that means the equation 12 of the transfinite interpolation corresponds to, that is the following. So the coordinates, function x, function psi and eta, first interpolated coordinates, they were interpolated between lower and upper. There we used 1 minus eta x1 of psi plus eta x2 of psi. So that was the interpolation between the lower and the upper boundary. And then we add the error, and the error, we have it still here, is 1 minus psi times the E3, and the E3, that was the error, that was the coordinate at the left, x3 of eta minus the interpolated values, and they were 1 minus eta xa minus eta xc. That was at the left boundary. So that was the error here that we subtract, so that we can retrieve in the end when we compose the correct left boundary. And similarly for the right boundary, we have the psi E4, and then the E4, that was the x4, the right boundary, x4 of eta, and we subtract then the error minus we subtract the interpolated coordinates. That was then between xd and between xd. So then we have this. So that is what we get in the end. And if we then choose, say, delta xi and delta eta equidistant for our example, then we would say we have would be in the middle, roughly like here. We have here and here some coordinates, and here and here. Then we could connect them, and they will then, well, we have to graphically do the interpolation a little bit here. be like that. Something like that. And also then lines which are connecting from the lower to the upper, and then from the left to the right would be similar. Would have something in the middle. Let's see. Like that, and maybe something like that. So then we can get some grids there, and we have also the possibility, if we do a different clustering, for example here, this would be a surface, you would want to have a clustering, then we can also do that by controlling then the choice that we do in the eta direction. And this control of grid points, that has been done and outlined by Lars Eriksson from first, he was at FFA, Theoretical Research Institute of Sweden, now has been for some time at Chalmers University in Gothenburg. And that is quite a useful method. One should be careful when you have large sudden curvatures. Well, that is not the problem. But in some occasions when you have a nose and you're not careful, you might get overlapping. So then you have to define the problem such that you restrict it to a smaller area so that you have better control of things, so that you avoid the overlap. But in general, this gives you a nice starting grid, and and sometimes you can even directly use it if you have some kinks in your geometry, where the geometry is changing the slope very abruptly, then that will also be reflected in the grid. So then the grid quality might not be that good. So in that case, one would need some method on top of that to get a smoother grid. But in general, this is a nice method to get grid generation for complex geometries with structured grids. So that is always the restriction. It's all restricted to structured grids. So that means the conclusion here is that the transfinite interpolation that is, we have seen before, that can often provide reasonable grids. And that what I said is the following, that however they are usually, so if you have a non-smooth boundary, then it will be reflected in the grid, so that they are not smooth. And references for that is where you have also the boundary control of the grid points. That is Lars Eriksson. And that is in AIAA paper in the journal volume 20. Exact reference. That is in 1982. They have generated with that very nice grids, both for external aerodynamics, like we have seen before, fiber aircraft, or also turbomachinery. What you can do when you have this, well, first an example here, that is from the book by Knupp and Steinberg. So they give here an example where you have defined then the boundaries, and where you then generate the grid just by the technique that we saw. And what I mentioned with the non-smoothness, that is this one here. So if you have a non-smooth boundary, here it's just a kink at the top and the bottom, then that will also be reflected by the grid lines in between. So then we have a jump in the angle. So the grid line, the angles are not changing smoothly, but there is a king. So that is not so good. What you can do then is you can use a different approach. Other than algebraic method, one can use then a differential approach. So, and that is then differential equation methods. And the most prominent of those are the elliptic equation, is the elliptic equation method. And that is due to Thomson and colleagues. They also wrote a book on that. It is cited in our textbook, Thomson et al. In 1985. So you see this is going back to the 80s. And in 2D we would solve two elliptic equations. In 3D, three. So two elliptic equations of the form that we have some coefficients, and these are our coordinates, and then we have here, we get second derivatives of x with respect to psi. So the indices now denote derivatives. Minus 2 beta x psi eta plus gamma x eta eta, and then we have some control terms p tilde and a first derivative of x with respect to psi, and then another control term q where we have x with respect to eta. But in the end it turns out that these equations have elliptic character, so you have to solve them in the way we have done that now for some time. For example, when we solved the heat equation without convection. So in here, it is not important to know all the details. It's just interesting to know that they are elliptic PDEs. So it's much more involved than just doing algebraic solve as we did with the transfinite interpolation. So these parameters depend on the derivatives x psi and x eta, and as I said before, the notation means that x psi is dx d psi, and dx eta means the dx d eta. So that is the notation here, and so on. And the p tilde and the q tilde are control terms. And you can imagine when we solve an elliptic equation, then we have a chance that we get it smooth. But it is much more costly than the algebraic approach. So that is the usual way, elliptic equation. There are also there's a possibility to solve hyperbolic equations, but that is an option, but it's mostly used for external aerodynamics. This elliptic approach is used much more. However, in the 90s, things started to change, because with this approach, with structured grids, as you saw in the example that we had before from the simulation of a fighter aircraft, we get extremely complex geometries, and when people try to do that with structured grids, they use blocks. But still, it was so complicated that the grid generation was the bottleneck in computational aerodynamics. So they took months to get good grids. So and then in the 90s, then people started to develop unstructured grid methods, which are much more flexible in grid generation. So and that is then also used today. And today we have also another approach emerging, that is that we have Cartesian grids, and that we represent the boundary on the Cartesian grid. Immersed boundary method, for example. So that is another possibility. But say for the applications, it's probably the unstructured grid approach that is used nowadays quite a lot. And the unstructured grids they have the big advantage over the structured grids that they have geometric flexibility. We can just, where we need it, we put in the points, we triangulize in 2D, we get a tetrahedral grid in 3D. So and we can put in more points where we need it. And that is also then very useful, that we can then do grid adaptation. So we can do the possibility of grid adaptation. Or if we have an unsteady problem where a shock is propagating, for example, then we can follow that shock and have good resolution around the shock. And when we don't need the resolution, we can get rid of that, and then we put the points where we really need them. And the other advantage, that is the advantage that has made it then now prevail, that it's much faster than using multi-block grid generation. Faster grid generation. Then for structured grids. However, nothing comes for free. There are also some cons to the method. And one is that unstructured grid methods are usually less accurate than structured grid methods. Less accurate than structured. So you have simply, when you have a very thin boundary layer, then it is much better to have a structured grid, because you can resolve that in a much better way. So when you have a surface, then it is much better that you choose really, as we discussed with the clustering function before, your grids such that you have one direction that is essentially normal. And not use here triangles, use quadrilaterals. If you are in 3D, then you use prisms. So you can still do a triangulation of the surface, but then you go out in prisms. So, and then you have then also these surfaces above, the grid surfaces above the surface of the wing, for example. And then you can also resolve that quite well. And that is what people do. For example, I would bet that they did, now you Stokes, that they did something similar on the unstructured part of the grid there, so that they went out in a structured way. So they have triangularized the surface of the wing, for example, it went out almost normal, so that they had a nicely defined normal direction. So then you can define the layers, you can resolve the layers much better than without. If you are then outside of the boundary layer, so this would be the boundary layer, then you can use unstructured grids. Then you can, whatever you like. But then it's for the accuracy not so critical. Critical are the labels. Another disadvantage of unstructured grid methods are that they need more memory. So they need more memory. Just when you think in 2D, if we think of, we have Ni by Nj cells, quadrilateral cells, then you just get the double already if you get triangles out of that. And in 3D it's even worse. If you use hexahedra and you cut them into triangles, you just need many, many more. So that are disadvantages, and you can see this disadvantage here by the fact that in a structured grid, you know your neighbors. If you have the index ij, you know where your neighbors are. It's I plus 1, I minus 1, j plus 1, j minus 1. In 3 dimension, k plus 1, k minus 1. Everything is clear. But in unstructured grids, you must give the program that information. You must provide the so-called connectivity. And that takes, of course, then also memory. So you need more points, and then you need more data for the connectivity. So connectivity information is required. For example, if you have an unstructured grid, then you have a couple of them. And you have some neighbors, what you like. And then if you number your cells, 1, 2, 3, 4, 5, 6, 7, 8, for example, then you must provide information on, for example, also the nodes. You have also then a numbering of the nodes, so they would then be something different. You would have node numbering. Let's see, you have 1, 2, 3, 4, 5, let's see, 6, 7, 8, for example. So they are the nodes. Then you have to provide this information to the program. For example, you have to provide what are the vertices of the cell number 3. So vertex of cell number 3. Say then the first vertex then is say is the 2. The vertex of cell 3, so this is the cell number. And the vertex number 2, if we go counterclockwise as we like in mathematics, so that is the number 7. And the vertex number 3 of cell 3 would then be number 6. So you have to provide this information. Also for the neighbors, what are the neighboring cells? So these are the vertices of cell number 3. Likewise, you would provide the neighboring cells, say the cell number of cell number 3. What are neighbors do we have? Number 2. Cell number neighbor of number 2 would be 4. And cell neighbor would be number 3 would be 7. So that would be the cell neighbors. computation with the finite volume. It depends. The data structure that is preferred now is a phase space. This would be then that we would need for a phase for a cell-centered approach. The vertices would then also be come in at some point, but often people now use a phase-based data structure. So they have then the data structure regarding to a phase. So then they say what are the end nodes and what are the neighbors. There is actually a program called Edge by FFA in Sweden. So that is then an information that has to be provided. Then you have, when you have this this information, you have your connectivity lists for the data structure that you have chosen. Then you do a triangulation. There is one called Delaunay triangulation. Delaunay triangulation, and that tries to get the most equilateral mesh. So, so given a set of points, so then that, of course, you have to choose in some of the points you have to choose, then a unique triangulation with the most equilateral mesh where the edges are most equidistant can be determined. So, and that is, if we have an example, if we would have 4 points, say we would have the chance to have a triangulation like that. That would be one option, or we would have the option to do it, have these 3 points. We would have the option to do it like that. So then this option would be more equilateral. So then we would choose this one here. And there's an algorithm for that is explained in our textbook by Fletcher and colleagues. That is the quote, the Bauer algorithm that does that. These details are not important, it's just to know that the principle, so that there is a mathematical tool, this algorithm that does the job. So that is one way. When you have the points given, then you can get it in this way. And another way, it's a more practical way, is called advancing front method. And that has the following idea. We start at a boundary. And so this is the surface. We start at the boundary. And then we decide on so how we choose the grid points on the boundary and what distance we want to go out of the boundary. So let me take little bigger ones. So let's see, we have something like that. So then we would have some triangles that we get out. And then we would continue on that. We would continue, that we have layers then that we let them grow, these layers. So and this is then our front. So then we march into that to the next boundary. So then we would proceed in this way. So we start from a distribution of grid points from the boundary, decide on a distance that we want to choose, and then we build up our triangles layer by layer until we meet the next boundary. And then the hybrid approaches I have already explained to you. Having a structured grid in the boundary layer and unstructured outside. And that is then a good way to have good resolution of boundary layers. Okay, so that is what I wanted to tell you about grid generation. I have one point in addition to that, and that is a point that we have not addressed here, that needs its own, has been addressed in its own, and that is how you can get the surface of a complex geometry. This is from a project that I'm leading now. It's on obstructive sleep apnea. That is when you sleep during night and the tongue closes the way from for the air through the mouth, and the soft palate closes the air through the nose. Then the people don't breathe for a few seconds, and then they almost wake up and breathe again. But this is extremely bad for the oxygen supply, as you can imagine, and it causes, it can lead to heart attack and to stroke. So people at St. Uller's Hospital, they want to know when they do operations in the nose, that is most easy, so that the flow through the nose is better, whether that helps a patient or not. And we, that is colleagues of St. Olaf's Hospital, and from the structural department here at NTNU, and from Synthetic Materials and Chemistry, and from us, Energy and Process Engineering, we try to provide a tool based on CFD. And what I wanted to show you is this example from my colleague Sverre Jonsson from Synthetic Materials and Chemistry. So he has got computer tomography screening data from a patient. Here we see some pictures of that. And then he retrieved the geometry from that. So that is the point that I did not mention. So you have to first get the geometry. And this is extremely complicated. This is the nose of the patient. Let's see, I have a point here. So it is, the upper part is the nose, and then the pharynx and the trachea. And we want then to do a simulation, and in the end we want to do a fluid structure interaction of the soft palate to see whether that makes contact with the pharynx. So you see, CFD is not only aerodynamics, but it's also biomechanics. Okay, so next week, the program will give you a summary of the course, and in the end, go through the last year exam shortly. You'll be given that later, but you can do that as a test for Wednesday, that you prepare the solution of yourself, and then you can see what it is like. And we'll have our last lesson on Monday. We have guidance for exercise 12 tomorrow at 6 to 8, but the last lesson will be on Monday. Okay, so then that's it.